the standard textbook for radio astronomy, but I was too busy doing other kinds of physics to pay any attention to it. And now, 50 years later, I wish I had read his book. But that's neither here nor there. So we'll press on here, and we'll talk about the history of radio astronomy. So we're going to start out with a little bit of perspective here. You know, everything we see in the universe either comes to us by way of electromagnetic force or gravitational force. And that's just a fact of life, you know, looking at it from a physicist's perspective. So in 1920 or so, we'll take ourselves back to there and try to establish our state of knowledge then. When you said astronomy, you meant visible light astronomy, because that's all we knew how to do, was look at the sky either through our eyes alone or aided by a telescope or binoculars. And those were the only detectors we had. And we were looking at everything through a very, very, very narrow piece of the electromagnetic spectrum. So when we talk about radio astronomy, what do we really mean? We mean electromagnetic wavelengths longer than far infrared. Now, you can argue about where that boundary is, and it's not a hard boundary, but approximately 100 gigahertz of frequency, and we're all radio people, so we think about frequencies, it is about where radio ends and far infrared begins. And some would say it's more like 300 gigahertz. That's okay. That's not much different. Why is that important? We'll talk about that. Okay, so the wavelength of 100 gigahertz is about 3 millimeters. And we talk about millimeter waves as being the shortest wavelengths of radio waves. And anything shorter than that looks like infrared. So radio telescopes don't look like telescopes. They look like antennas that as radio people we're all very familiar with. Telescopes for shorter wavelengths usually look like lenses. So that's sort of the distinction there. So why do we do radio astronomy? Okay, so radio astronomy illuminates, and I'm using that in a funny way, features of the universe that are not apparent from other forms of astronomy. Okay, and it allows us to see features of the universe that add to our knowledge of how the universe works. And that indeed, I think, in a macro sense, is the reason we do science at all, is to find out how the universe works. Einstein said, my job is to read God's mind. And I don't think you can get any more specific than that. So we're trying to figure out how the universe works. And up until the period from 1920 to 1930, the only tools we had for looking out into the universe were our eyes and spectroscopes and other things that worked pretty much in the visible wavelengths. So here's a very, very cursory, top level, 30,000 foot look at the electromagnetic spectrum. Okay, and it goes from, if you look at the bottom, we have the longest wavelengths are radio waves that we're all familiar with, since this is the National Capital Radio and Television Museum. We're all familiar with those. And the top end of radio waves is microwaves, and they're really radio waves because they behave pretty much like radio waves. Above microwaves, we have infrared, which manifests itself to us as heat. We can't really see it, but we can feel it. Then we have near infrared, which is just the infrared that's close to visible. And then we have the visible part of the spectrum. That's a really tiny part of the spectrum. It only goes in wavelength from about 750 nanometers to 400 nanometers. And a nanometer is a billionth of a meter. Okay, so what we can see with our eyes is really a tiny, tiny bit of the electromagnetic spectrum. At shorter wavelengths, we have ultraviolet, which is again light that we cannot see that does nice things like giving us sunburns. A shorter wavelength than the ultraviolet, we have X-rays, and X-rays are just X-rays. And at shorter wavelengths than X-rays, we have gamma rays. And anything with a shorter wavelength than an X-ray is a gamma ray. Nothing with any shorter wavelength has a different name. That's the electromagnetic spectrum. And at the bottom, you can see a little graphic that shows wavelength and what all those different kinds of radio waves are, what all those different kinds of electromagnetic waves are. Let me make a point right here. These are all electromagnetic waves. They all have the same characteristics. They all satisfy Maxwell's equations. And astronomers explore the universe in all these regimes. But tonight we're going to talk about radium. Very short, one slide physics lesson. Okay, so quantum mechanics tells us that electromagnetic radiation exhibits properties of both waves and particles. All electromagnetic radiation does this. Everything from radio waves up to gamma rays. Okay? At the radio end of the spectrum, wave properties dominate. And of course, we're all used to dealing with radio as radio waves. We don't talk about radio photons, although they do exist. They're very low energy photons, but they do exist. At the gamma ray end, particle properties dominate. Gamma rays look more like little bullets. We don't really talk about the frequency of a gamma ray. We talk about its wavelength, or physicists like to talk about gamma rays and X-rays in terms of the energy of the individual photons. But they're all electromagnetic radiation. Now, the reason that we do astronomy at all these different wavelengths is that the universe responds to electromagnetic radiation of different wavelengths in different ways. And different wavelengths allow us to see different things. Okay, so pre-World War II. Let's go back to the 1920s and 30s. Bell Telephone Labs was searching for the origin of static that affected radio communications. You know, history of radio communications, as we've seen, we talk about the guys like, if you saw Ken Burns' wonderful film, Empire of the Air, you see that E. Howard Armstrong invented FM as a way to get around static on AM. And noise is always a problem. So radio engineers are always looking for noise, trying to characterize it, figuring out ways around it. So a Bell engineer named Carl Jansky built a 100-foot by 20-foot antenna and pointed it up at the sky. And no surprise, he got a lot of static on it. Jansky found static from thunderstorms, but he also found a steady hiss that reached maximum intensity every 23 hours and 56 minutes. And, that's the period of Earth's rotation. So every 23 hours and 56 minutes, his antenna was pointing right at something that was squirting noise into it. So at that moment, radio astronomy was born. And Jansky didn't realize it right then, but he was the first radio astronomer. Here's Jansky's antenna. It's about 100 feet by 20 feet. It's on a rotating pedestal. This is a replica of it that exists at Bell Labs in New Jersey, I believe. And Jansky rotated his antenna by the simple expedient of attaching a rope to it and pulling it around in circles with his Model T Ford. So Henry Ford had a big part to play in the origins of radio astronomy. So we've got the Jansky hiss, or as it's called by astronomers, the Jansky noise. So at first, Jansky thought it was radio noise from the sun. So he did the best he could at pointing his antenna at the sun, which mostly involved waiting till the sun was right overhead. And that didn't really do anything. The noise was pretty much the same. But he did figure out that the signal was strongest in the direction of the galactic plane, the center of the Milky Way. So now we know that the noise actually comes from a 4 million solar mass black hole at the center of the Milky Way called Sagittarius A. Now you have to realize in the 1920s, it was not commonly recognized that the Milky Way is our own galaxy. Black holes were predicted by general relativity, but nobody had ever seen one. Well, you really can't see one, but nobody had ever detected one. The scale of the universe was unknown. The man on the street thought that the entire universe was the solar system. And only astronomers knew that the Milky Way was made up of stars, didn't really know how many. And until Hubble did his work in the mid-1920s, it wasn't recognized that other things besides the Milky Way, like Andromeda, were actually other galaxies. So we were at a pretty low level of understanding of the cosmos in the 1920s. And radio astronomy helped us get a better understanding. So now I'm going to switch over to another radio astronomer who didn't really know he was a radio astronomer first, named Grote Reber. Now, all of you guys who are radio amateurs and are proud of your long wire antennas, I want you to look at that gadget behind Mr. Reber there. That's an antenna that he built in his backyard. So when you're proud of your wire antenna, think of Grote Reber building that contraption, 30-foot parabolic dish in his backyard. He later moved it to the National Radio Astronomical Observatory in Green Bank, West Virginia, where it sits to this day, and did some very elegant landscaping around it with garden plants, which you can see in the picture. Now, Reber could move his antenna in azimuth and elevation, so he could map radio emissions from a broad swath of the galaxy. And two of his original contour plots from 1943 are reproduced on this slide. And the photo is from the National Radio Astronomical Observatory, and the contour plots came from Sky and Telescope magazine from 1949. So Mr. Reber was quite an innovator, and I'm sure his wife watched him for many, many months as he put his radio antenna together, and probably thought that he was going out of his gourd doing it. But he made the first real structured contributions to radio astronomy. So what did he discover? He discovered there are a lot of very intense radio sources in the galaxy and outside the galaxy. And he discovered what was later determined to be Cassiopeia A, which is a supernova remnant that is a great radio source. And all satellite communications engineers know Cassiopeia A because that's what you use to calibrate your dish antenna. Cygnus A, a radio galaxy, nothing particularly remarkable about it except it gives out a lot of radio energy. Puppis A, another supernova remnant. These sources are commonly used in calibrating radio telescopes and communications equipment, since their locations and strengths are known with great precision. And when I was working on satellite communication systems, we would point our antenna at Cassiopeia A all the time. It's a real nice one to use because it's always high in the sky. And the nice thing about radio astronomy is you can do it during the day. And of course, if you're a stellar astronomer, you're familiar with the chair of Cassiopeia. A is one of the stars in the chair. And here in the Northern Hemisphere at mid-latitudes, Cassiopeia is always visible 24 hours a day. You can't see it in the daylight because the sky washes it out, but it's there, way above the horizon. It's one of the circumpolar constellations. Big W in the sky, can't miss it. Okay, another guy here coming along to the 1940s, James Hay. found radio signals originating from the sun. And we're all aware of the 10.7 megahertz radio spike that comes out of the sun that we use to measure solar sunspot activity. The signals originate in electrons whirling around magnetic fields associated with sunspots and in solar flares. Now, right now, we're at a solar minimum, and it's a minimum. And I do have a solar telescope, and I occasionally look at the sun through it. And there are very few sunspots out, which is one of the things that's making propagation for us radio amateurs so crummy. My friends who are solar astronomers tell me it's their guess that the next solar maximum isn't going to be much more maximum than the current solar minimum. So if you're a ham radio operator, don't bet on anything getting much better in the next 11 years or so. So World War II, okay, a lot of science that wasn't particularly concerned with winning the war went on the back shelf. But World War II, as wars do, did spur rapid development in microwave electronics, antennas for radar, communications, and the radio astronomers saw all this going on, and they gathered up what they could from it. And after World War II, radio astronomy really, really took off. Okay. So fast forward to the 1960s. Cambridge University in England, astronomer Jocelyn Bell discovered evenly timed radio signals coming from deep space. So her boss was initially skeptical because Jocelyn was a very young scientist, postdoc, and he thought that she had simply screwed up the experiment. But eventually he understood that these signals came from a rapidly rotating magnetized neutron star, later named a pulsar. And in some irony, Jocelyn Bell's boss got the Nobel Prize for this. Jocelyn did not. She's still alive and purports to be not bitter at all about that, which tells me she's a really big person. Her boss got the Nobel Prize, but she found the thing. Okay, so that was one of the big initial discoveries. There's a pulsar. It's a thing that nobody saw coming. Okay, the radio astronomy found it. Quasars. Okay, 1953, Geoffrey Burbidge, another British astronomer, theorized that synchrotron radiation could come from charged particles rotating at relativistic speed along magnetic field lines. Okay, I would say, the word that the article used was theorized. I would say hypothesized. It was a fine point, but it was a hypothesis. 1963, a team of scientists demonstrated that a star-like pinpoint of light with the wonderfully eponymous name of 3C273 was actually more than 1 billion light years away and was producing synchrotron radiation. So again, this gave us a scale of the universe that we didn't know. We didn't know the universe was 1 billion light years wide until scientists found quasars. And over the years, they found many, many, many quasars. Quasar means quasi-stellar radio source, because it looks like a star to the sky, but it's a tremendously intense radio source to the radio astronomer. So we know quasars are supermassive black holes that emit streams of matter at relativistic speeds. What's a relativistic speed? Well, a relativistic speed is a speed that's a large fraction of the speed of light. Now, this is matter going at a large fraction of the speed of light. And what special relativity tells us is that it takes a lot of energy to get a little bit of matter going at a large fraction of the speed of light. So quasars are very, very energetic things. So we didn't have any theory that predicted the existence of quasars, but we found them. And bingo, the theory had to accommodate that, as happens in science. And quasars are among the oldest objects observed in the universe and help us establish the size of at least the observable part of the universe. The distinction between the observable part of the universe and the whole universe is probably worth an hour presentation all by itself. I won't get into that too much. Okay, gravitational waves. The other big macro force in the universe besides EM is gravity. Okay. Now, gravity and magnetism are two different things, but they do share one property that's very interesting, and that both gravity and magnetism move at the speed of light. If somebody grabbed the sun and jerked it 1,000,000 miles left right now, the Earth wouldn't feel the jerk for about 8.5 minutes. That's how long it takes the gravity wave to get here. We didn't know this until, I don't know, the last 20 years. There was speculation, since gravity is so much weaker than electromagnetism, we hadn't observed gravitational waves enough to know this. So the Very Large Array in New Mexico, which is now named after Carl Jansky, has played a part in studying gravitational waves, because when a gravitational wave event is detected, scientists then look at the direction of that event, from which that event came, in other phenomenologies like electromagnetic waves. So the Very Large Array is part of a very large extended array of telescopes that act as an interferometer and can be used for determining directions of signals. So the gravitational waves that have been observed have come from a titanic collision of neutron stars in a galaxy 130 million light years from Earth. Neutron stars are super dense objects left over from massive stars that have died. They're magnetically active and very strong gravitational fields. When they collide, they send out gravitational waves, but they also give off strong radio emissions. That's what the VLA and the Australian Telescope Compact Array and the giant meter wave radio telescope in India are combined to study from 3 distinct parts of the Earth. And scientists got new insight into the phenomenon behind the creation of gravitational waves, which again is another block to check on our understanding of how the universe works. Exoplanets. Okay, we found a lot of exoplanets with sensors like Galileo orbital telescopes. And we also have done some exoplanet research in radios. Sub-millimeter wave telescope arrays like ALMA that I'll talk about in a couple of minutes can see more detail than optical infrared telescopes because the longer waves are not scattered or reflected by interplanetary dust and actually penetrate our atmosphere better. And plus, you don't have to, the star isn't glaring at you, so you don't have to block it out. The physical part of the star is pretty much invisible in the radio spectrum. So ALMA can see planetary systems in the earliest stages of their formation. Another clue as to how the universe is built. Let's talk about hardware for a little bit, okay? Weak signals require large antennas. Back talking about radio again. So the Green Bank, West Virginia antenna is 360 feet in diameter. If you ever get a chance to go out there and see it, I recommend it. That is a really big thing. And if you like me, like big things, that's a big thing. That little dark gray rectangle at the bottom is the building that the antenna is controlled from. So that's a big honking antenna. 59 dB of gain at 1 gigahertz. This antenna is fairly new. I think it's about 40 years old. It replaced the previous antenna, which was a little smaller, and one night just collapsed all around the building. There was an astronomer in the building at the time. He was not injured, but he was very, very much shaken up and required the administration of several bottles of single malt scotch to bring him back to life. Green Bank is owned by the National Radio Astronomical Observatory, the United States government, and they rebuilt an even bigger, better antenna. That's a big thing. Go see it. That's, by the way, the Green Bank is in the middle of what's called the National Radio Quiet Zone. So if you're a ham radio operator, turn off your HT before you go out there. So I see Jim shaking his head, right? So you know all about that. Yeah. So don't transmit near the Green Bank, because they might think you're an alien. Okay, Arecibo dish, located in Puerto Rico, not movable with relation to the Earth, 1,007 feet in diameter, 68 dB a gain at 1 gigahertz. Can be used for receiving, transmitting, SETI, primarily a science radio telescope. Right now it's out of commission because about 3 weeks ago, a part of that structure that you see there collapsed with a big honking dent in the dish. So it's going to be down for quite a while it's being repaired. Here's the latest and greatest big stuff piece of hardware. FAST, the 500-meter aperture spherical telescope. Located in southwest China, not movable, 1,640 feet in diameter, 72 dB a gain. Boy, radio guys just go crazy. What would you give for 72 dB a gain? Most of the satellite comm engineers I've worked with would give their kids up to 3 dB a gain. It also does SETI, as I mentioned during the SETI presentation, but it is primarily a science radio telescope. So pointing limitations. Arecibo and FAST and some other big dishes are not independently movable. You can move the receiver array a little bit and kind of direct them a little bit, but not really. So in order to move the antenna, you have to move the Earth, which means you have to wait till the Earth is pointed in the right direction to get your observations. So that makes radio astronomers a patient sort. But they're very lucky because they get to work during the day. They can work at night too, but if they want to, they can work during the day. VLA, I've been out there. I was working on some radio projects out in near Socorro, New Mexico. And one day I decided to take a day off and go up and look at the VLA, which is up near Socorro. 27 antennas. They can be tightly clustered or separated by up to 26 miles. And if you're all familiar with that part of New Mexico near Socorro, if you want to move things around 26 miles apart, you've got plenty of space to do it because there's a whole lot of nothing out there. It was in the movie Contact. It's another thing that if you're ever driving through Socorro, New Mexico, I don't know why you'd do that, but if you ever do, get out and see the VLA. It is really cool. You can drive out there. There's very seldom any people out there. It's just you and the buzzards. And it's really something to see. If you're really lucky, like I was on the day I went out there, one of the antennas will be moving. And they move under computer control. I mean, moving from place to place. And I watched one of these antennas trundle across the horizon.
Wow.
No people involved at all. It's really something to see. Those are big antennas. The dishes are 82 feet in diameter. They're pretty big things. So they have a little locomotive that pulls them around, but nobody driving it. ALMA. Okay, ALMA is in northern Chile, in a place that's very dry and very high. So there's not much atmospheric stuff to get in the way of radio signals. The Atacama large millimeter submillimeter array, it's located in the Atacama Desert, where there has been no recorded rainfall in the entire time that humans have been out there looking for it. So it's a pretty darn dry place. Got to bring your own water with you. So ALMA is a science radio telescope array. and it does sub-millimeter wavelengths, and it studies the expansion of the universe. The VLBA, Very Long Baseline Array, is a network of 10 observing stations located across the United States. They go from Hawaii to the U.S. St. Croix and the U.S. Virgin Islands. There's a string of them. And the whole baseline is 8,611 kilometers long, which gives you effectively an 8,600 kilometer diameter antenna. Now, you don't get all the benefits of an antenna that big, but you do get one important thing, and that's resolution. You can really, really, really get good angular resolution out of the VLBA. And the VLBA data is analyzed at the VLA in Socorro, where we have a giant computer known as the correlator. Sounds scary, doesn't it? You know, if you step out of line, I'm going to send you to see the correlator. Ooh, don't do that. Okay. But what the VLBA gives us is great, great, great angular resolution, even better than the VLA. So we've talked about what radio astronomy is and what some of the hardware looks like, not all of it. This is just a survey. But what are the big puzzles that radio astronomers are looking to solve? Well, one of the biggest ones is the expansion rate of the universe. And we've been dancing around this one for over 100 years. Because when Einstein put the little red ribbon around the general theory of relativity in 1915, he realized that the general theory predicted that the universe was either expanding or contracting. Now, Einstein didn't believe it did either, so he inserted a fudge factor into his equations to keep the universe from expanding or contracting. And he was pretty proud of that until Edwin Hubble came along, found the redshift and said, no, it really is expanding. Okay, so how do we tell how far away something is in the universe? We use a standard candle, a bright event that unfolds exactly the same way every time, called a type 1a supernova. That's one of them, and the other is Cepheid variable that Edwin Hubble used. And if you know how bright something is, and you measure how bright the thing you're looking at is, you can use a little simple mathematics to tell how far away it is. Okay. Dark energy. There was a little problem with using the standard candle. The supernovae were too dim at the distances they were supposed to be. The brightness and the redshift didn't match. Okay? So what that told us was our understanding of the expansion of the universe is wrong. And it's wrong to this day. And there are a lot of competing hypotheses right now as to why our knowledge of the expansion of the universe is wrong. So this is one of the big problems that radio astronomy is trying to help solve. And there's a couple of Nobel Prizes buried in here for anybody that wants to take a crack at it. So if you have kids or grandkids that want to be astronomers, tell them, well, yeah, but you know, the visual spectrum is so boring. Go into radio astronomy. That's where you're going to make your money. That's where you're going to get your Nobel Prize. Dark matter, okay? There's a lot of missing matter in the universe. Another thing the expansion is telling us, there's a lot of stuff, just plain old stuff in the universe that we can't see. Something is holding galaxies together more than the gravitational attraction of the 100 billion stars in a galaxy. There's a lot more stuff out there. We have found huge halos of invisible hydrogen gas, but even that's not enough. So we're still looking for the dark matter. The problem with the dark matter is it's dark. You can't see it. Well, radio astronomers are looking for it in the radio spectrum. With the visible spectrum, there just ain't anything out there. So, summary of my presentation. I'm a few minutes ahead of schedule, so we got time for questions. So, radio astronomy gives us a way of looking at the universe that's different from what we can see with our eyes, and can teach us things about the universe that our eyes cannot. So, visible light astronomy is thousands of years old. You know, we have visible observations that go back to early Chinese history, back to the Sumerians, back to Arabs from way before the start of the Common Era that we count our years from. But radio astronomy is only about 100 years old. So there's an awful lot more to do here, and very fertile ground for people to study. And I would be remiss if I didn't mention at this point that astronomy is also carried on in infrared, ultraviolet, X-ray, and gamma ray wavelengths. And NASA has either has missions up now or will have missions up now to study the universe in all those spectra, and we have done that. And the Webb telescope, if it ever gets off the ground, is going to be an infrared telescope. It is an infrared telescope. It just happens to be sitting in California right now instead of out at the Lagrange point where it belongs. So that puppy is supposed to launch in 2012. Oh, wait, no, we missed that. 2017. Oh, darn, missed that one too. 2019. Not quite. I think 2022 now. Is the latest guess to when the Webb is going to get going. But my son works at Goddard, and the Webb was there for testing, and my son got me in to see it. And that's one of the best things he ever did for me besides being born. And I got to see the Webb telescope all unfurled in a room at Goddard. And it's big stuff. It's a big, big, big telescope. And it's going to be really scary to unfold that thing in space. But I have confidence in the NASA boys. They're going to get it done. Okay. That's the end of my presentation. So I'm open for questions. And like I said, I'm not an astronomer, so I'll just do the best I can. Go ahead.
Please unmute if you have questions.
Excuse me?
Please unmute if you have questions, if anyone has any questions.
Okay, Rich, I was visited Green Bank in the early 70s, and they had, you were talking about the reference stars or supernova remnants. They had a, it was about 8 or 12 feet across square horn that was about 100 feet long on the side of sitting on the side of a hill, pointing up so that once a day it pointed at one of those radio sources. My friend said it was the Cass A star, but I think it might have been one of the other ones because they think the A star varies more.
Yeah, that's a nice efficient way of doing it. You don't have to move your big honking 300-foot antenna around. You can get your signal off a much smaller antenna. And those things are really bright in radio. And if you have a directional antenna, you can pick them up. I don't remember right now what the radio spectrum looks like, but you can look it up, and you know, you might be able to pick up the noise with you know, with an amateur receiver. It's nothing really dramatic, but it can be done. But thank you for telling us about that. It's interesting hardware. Anyone else?
Rich, can you tell us what happened, the damage to Arecibo?
Yeah, as I understand it, one of the support cables for the the center array, the focal plane array, well, I'm talking like an optical telescope. The feed that's hung out over the dish in the middle, it's a Cassegrain kind of thing. One of the support cables broke. Those are pretty big, beefy cables because they're 500 feet long. And it came crashing down and it just went right through the dish. I saw a picture of it and it's a real mess. Engineers are out there right now figuring out how to fix it. The Arecibo people said it's going to be down for months. My guess, looking at the mess that it was, maybe more like years while they fix it. Because it's going to be very expensive to fix. Nobody got hurt, thankfully.
Yeah, the cable that broke was 3 inches in diameter.
That's a big piece of cable. You don't want that hitting you in the head.
Oh.
Any other questions?
The picture from the air didn't show that much damage. It was like less than 10% of the dish, but the picture they show in the magazine was like from below that showed this huge gap. And it was a huge gap, but it wasn't 1,000 feet across. It was about 100.
Yeah, it looked like it took out a big chunk of the dish. Yeah, from what I could see, I did see the ground picture. And, that's too bad. A lot of science and a lot of SETI isn't going to get done until they get that thing fixed. Because one of my goals was someday to get down to Puerto Rico and see the dish, but I don't know if I'll ever do that. I'd like to get out to China and see it, but I'm afraid if I go to China, they won't let me out. So I'm going to stay here, just look at pictures. Any other questions or comments?
I think I've heard that Arecibo is finances are really shaky.
Oh, they always are. Yeah, Arecibo is always scrounging for dollars. When a big event like this happens, the big question is, can we even afford to fix it? Is it worth fixing? And of course, I think, yeah, it is worth fixing. Because Arecibo's annual budget wouldn't buy a set of spare tires for an F-16. That's really not part of the equation. You talk about budgets. I started out my career. I had the best job I ever had when I got out of college, and I worked on the Apollo program. And at that time, NASA had 10% of the federal budget, and Apollo had 90% of NASA's budget. And right now, NASA's budget is something like, I don't know, 1/3 of 1% of the federal budget. And NASA's talking about going to Mars. So, Mars is going to be a bigger relative chunk of change than Apollo was. So while you're on Netflix watching that show Away, think about how much all that's going to cost. Wow. Okay, any other questions? Okay, I'll be here for a bit. Again, if anybody has any questions, give me a shout. And I'll be happy to answer them if I can. Again, I am not an astronomer, but I know astronomers, so I can get an answer to just about anything. So I want to thank Charisse and Brian again for letting me do this. I'll be back at some time in the future with another presentation. And I have 1 or 2 more planned that I'm working on. I thank everybody in the audience for being such a good audience and for staying up to watch my presentation. And I just have a blast.
Thank you so much.
Thank you.
Thank you.
Thank you,
Thank you.
Rich.
Well done, Rich.
Thanks, Rich.
Thank you.
Excellent, Rich. Thank you.
Thanks for setting this up.
Thanks, Rich.